Okay. So it's my pleasure to introduce Zoltan Bajnok, who will speak about Octagon resurgence. Please, Zoltan.
So, thank you very much. So, once more. Yeah. So, thank you very much for the kind invitation. It's my pleasure to be here. And thank you also, Didina, for introducing this Octagon object. And I would like to actually, this talk, to expand that strong coupling, that object. So that's the idea of the talk. This is a work in collaboration with Grisha Korchemsky and my very talented PhD student, first-year PhD student, Berzer Boldish. So the work is on the archive, and then it was accepted in PRL, and it was chosen as a PRL highlight. So we are very happy about this. So in the previous week, thank you for the invitation also for that part. We learned how integrability actually met Bootstrap. And then there were some discussions on the afternoon, and one discussion was led by Kolya, and he provoked us asking what we think, each of us actually interviewed us, what we think is the most fundamental challenge in theoretical physics. And the mass gap was already taken when I answered, so I answered, I think it's the resurgence structure of QCD. So I would like to explain actually today what I meant by this resurgence structure. So I'm listing here perturbative expansions into theories. On the left, you have QCD. On the right, you have N equals 4 super Young-Mills. And here, what I wrote is basically the quark mass anomalous dimensions. It has been calculated up to 4 loops, and you can see the result. Well, can you? So you can see some odd zeta functions, even zeta functions, and these expressions grow. And if you would evaluate numerically, you would see that they are really growing. And for example, if you would like to use the same result to calculate muon decay or tau decay using the Adler's function of QCD, then you would see that these coefficients really grow like factorial. And the general form which is expected is something like this. So it's like a factorial growth, some power of Cn, it's a power of n, maybe n to the alpha and some constant. So this is what is expected. But unfortunately, in QCD, we have only these 4 terms. So we cannot really analyze what are those numbers. So that's why we would like to switch to some theory when we can go much more beyond. And this is N equals 4 super Young-Mills. Here I'm cheating a bit because on the right-hand side, you see a strong coupling expansion. I could expand the observable, what we learned just in the previous talk, also at weak coupling, and I would see this perturbation theory is actually convergent with a finite radius of convergence, which is the same what you would see in the dispersion relation. So it's a strong coupling expansion, but otherwise very similar. So you have log2 terms, you have odd zeta functions, and then here in this theory, we can actually calculate a lot more coefficient. And this is what I would like to talk about. Here you can see if you calculate many, many more coefficients, it's really growing like factorial. I would like to first comment a bit about this ADS-CFT duality, that it's more like a triality than a duality. This is how I would like to start my talk. And then I will turn to this octagon form factor, what Didina already introduced. But I would like to show you that there are many other observables in N equals 4 and N equals 2 super Young-Mills theories, which can be written the same infinite determinant form. And we will develop a machinery which works all of these determinants in the same time. These determinants are the generalizations of these Tracy-Widom distributions. And I would like to make a strong coupling expansion. We will calculate many, many terms, and we will see this factorial grow. And some part of the talk will explain what to do with a perturbative series which grows like factorial, how to give a meaning of that series. that is going to be Borel resummations. And that Borel resummation immediately will lead to non-perturbative corrections. So this is one of the take-home messages, that if you have a factorially growing perturbative series, then you will have non-perturbative correction. And in the observable, you have to include those non-perturbative corrections too. And then I will conclude at the end. So just very quickly, it would be nice to do the calculation in the standard model or QCD, but that Lagrangian is very complicated. It will fill an A4 page. So instead, we would like to do the calculation n equals 4 super Young-Mills, because it has only two parameters, the number of colors and the Young-Mills coupling. And when we do perturbation theory, this is what we usually do if we are given a Lagrangian, then we do this perturbation theory in the 't Hooft coupling and also in 1 over n. And in my talk, n is going to be infinite, so I will work in the planar limit. So this is the comment about this triality. So if we had got only just the super Young-Mills theory, then what I would do, it's a conformal field theory, so I would like to calculate some observable. So I'm talking a bit about the spectral problem. So I would like to calculate, say, the two-point function. The two-point function is given in terms of the scaling dimension. The scaling dimension in the planar limit is a function of the 't Hooft coupling. And what this gauge theory will give us, it will give a perturbative expansion in lambda. So it's a series expansion, and then using maybe a little integrable spin chains, we could calculate a few orders, okay? But not more. So doing this calculation, we will get a few perturbative orders. And there is this conjecture that this is actually dual to string theory on ADS5 cos S5. So what string theory gives, then typically we identify some minimal first surface, we calculate the surface, we analyze the fluctuations. So it's going to be an expansion in 1 over square root of lambda on the string theory side. And then if we had only these two theories, and then that's really a conjecture that these two series expansion with not overlapping validity ranges describe the same function. But I would like to emphasize that this is actually a triality. So we have Young-Mills on one side, string theory on the other side, but we also have a 1 plus 1 dimensional integrable bootstrap description of this whole theory. So we can interpolate, we can calculate an exact solution. So integrability works differently. It works in the size of the operators. You go to infinite size, you bootstrap the S matrix, which is valid for any coupling, and then you take into account the finite size correction. For example, that operator can be described by a multi-particle states, and you start to calculate asymptotic beta ansatz, then finite size correction, virtual particles, and then you can resum by the thermodynamic beta ansatz or the quantum spectral curve. Once you have this exact description, this quantum spectral curve, then you can expand the quantum spectral curve at weak coupling, and you can recover analytically this perturbative gauge theory numbers. And then you see that really in the small coupling regime, the quantum spectral curve, the integrable description reproduces the Young-Mills. And of course, you would like to do the same as strong coupling. And then we had this first talk in this conference when Simon tried to do it analytically, and still it's not possible actually to do an analytic expansion. We could do it numerically, and numerically we can see that it really fits with string theory. So this is kind of proof that really these two theories are the dual to each other, and then this duality is made explicit by this integrable exact description. Okay? So we would like to do something similar for another observable. And this is the observable, what Gina already introduced. This is a 4-point function. So we would like to calculate a 4-point function of half-wave BS operators, like z to the k, x bar to the k. It appears twice. And then you also have trace x to the k, z bar to the k. So we calculate these 4-point functions. And of course, it's a function of the conformal cross ratios. But what is nice about, thanks to Frank for this operator, that if we send this k, the size of the operator, to infinity, then this 4-point function will factorize into two factors of the same form. So it's a total square. This is the square of the octagon. And then we can, using Yang-Mills theory calculation, we can actually calculate the perturbative expansion at weak coupling of that octagon observables in terms of letter integrals. And then I'm switching from the Toft coupling to this G. So you can make a small G expansion, and that's what this Yang-Mills theory provides you. So this is at weak coupling. On the other side of the duality or the triality, you could do a string theory calculation. So you could calculate the geodesics and then the minimal surface in string theory, and then you could analyze the small fluctuations. So this will provide a strong coupling expansion of your observables. Again, these two descriptions have no overlapping domain. So we need integrability. Integrability, Didier very nicely explained, that you can actually calculate the same quantity for all coupling using integrability. Because we send this k to infinity, then this worksheet basically the square of the front and the back worksheet, and then you can hexagonalize this worksheet, inserting a complete system of states, and then you can sum up all these hexagon amplitudes in these two cases. Once you sum up, you will get an infinite, semi-infinite determinant. So that observables, which interpolates between these two descriptions in the Yang-Mills at weak coupling and the string theory at strong coupling, it's an infinite determinant. It's the infinite determinant of this form, where we have this product of Bessel function, n minus 1 to n minus 1, and then some function, which is a function of these conformal cross ratios, and then it's just reparameterized in terms of this y and psi, and it's explicitly known like this. So today, we would like to make a strong coupling expansion of that determinant. Okay, so it's better than the spectral problem because we can actually calculate analytically the strong coupling expansion, and we can compare to string theory. Weak coupling, it agrees with gauge theory. I would like to slightly generalize this determinant, introducing this curly L. This is related to the previous talk when like L particle propagates in the fusing the hexagons. So this is a slightly different observable when I shift with some integer these Bessel kernels. So my semi-infinite determinant will depend on the G and this L. I can think of this matrix element, this K and M, as a matrix element of some integral operator between Bessel function as basis function. They are orthogonal actually, this inner product. And this is called the Bessel kernel, so it's a function of x and y. This quantity here is called the symbol of the Bessel kernel. So this integral operator is very well known in the mathematical literature. It's called the Bessel kernel, and that's the symbol. And we have seen that the octagon amplitude, what we would like to expand, can be written in terms of the symbol in this particular way. So what is nice about this is determinant, that it appears for many, many observables in n equals 4 and n equals 2 super Yang-Mills theories. So I'm just listing the few. First, it appeared for this Tracy-Widom distribution, which described how the eigenvalues behave near the hard edge in the Laguerre ensemble. So if you choose your symbol like a step function, then that determinant describes the Tracy-Widom distribution. This is a well-analyzed quantity in mathematics. If you choose it like 4 over x squared, then this describes the expectation value of the circular reason loop. If you choose this other form, then it describes a flux tube correlator. It can also describe the 1 over n squared correction of the free energy on an n equals 2 super Yang-Mills theory. With that kernel, so changing this symbol, changing the kernel, you can describe many interesting physical observables. You can think of these other integrable observables as a generalization of this Tracy-Widom distribution, where instead of having this hard cutoff, you cut off the integral with in a smoother way. In the previous talk, we met this octagon amplitude when both y and psi was 0, and also in my talk, I will consider on this particular case, when the symbol is just this form. So the first nice result, it's a bit technical, it was done by Andrei Belitsky and Grisha Korchemsky. They managed to calculate a strong coupling expansion of that determinant. The way they did it, I'll just quickly explain. So the first few terms actually they were calculated already by mathematicians starting from Szegő during the First World War, and then later extended a few more terms. Mathematicians were not very much interested in this 1/g corrections, but in physics it's interesting for us. So Andrei and Grisha figured out how to calculate it. The way they calculate it, so you have these perturbative corrections, and then you parameterize this perturbative correction, and then you realize that the resolvent actually satisfies a very nice differential equation with a potential which comes exactly from this second derivative of the logarithm of the determinant. And even more, if you solve this differential equation, you plug back to this integral form with this derivative of the symbol, then it's also related this logarithmic derivative of the determinant. So taking this ansatz, solving the differential equation, and demanding that after integration it will give back the same thing, this fixes all these coefficients. So this is the way how you can make an exact 1/g expansion of that determinant. That works for any symbol. So we haven't really used here what the symbol was. So the strong coupling expansion is completely written in terms of the moments of the symbol. So once you know your symbol, you can calculate all these moments, and you can express all these expansion coefficient in terms of the symbols. What appears is this L parameter, and additionally what is relevant, how this symbol approaches 1 when x goes to 0. This is this exponent, this beta appears, and this L, this shift parameter in the determinant appears in this combination, and then these are the first few terms what I'm presenting here, but in principle you could calculate many terms, okay? And then the first guy appears only here. In the later you will have log2s and odd zeta function. And then you remember at the beginning I showed some coefficients, so you can generate those coefficients, and from this form you see only those guys will appear. There is some interesting relation actually between different observables. So there is this octagon observable, the localization observable, and this cast related observables. And then because they are in the moment, the logarithmic derivative of 1 minus chi, if you calculate, then you will see this relation. This implies actually that the octagon, if you make a strong coupling expansion of the octagon, then and if you change the sign of that octagon, that will describe the localization result. So it's two different observable, two different theories. Why they should be related in this way, it's not clear, but they are. Okay, so what can we learn? So we made this strong coupling expansion, and then what can we learn out of it? So maybe a small comment. If you rescale, you change your coupling a bit, you shift, then you can absorb actually all the log2s. And then there are no log2s, only odd zeta functions. So we have these many terms, and then you can draw them, but they are growing and growing. So imagine an expression where all possible combination of odd zeta functions appear. And then you calculate 30 terms, and it cannot even fit to your computer. So how can you figure out some physics, extract some physics out of it? And the idea is that instead of restricting on the analytical expression, let's play a kind of numerical mathematics, numerical experiment. So let's calculate 400 perturbative coefficients for like 1,000 digits. And then let's see what can we extract from these numbers. So what you can do, you can see how they grow. And then what you will see, they grow like factorial. So if you take your coefficient, what we just calculated in the strong coupling, if we divide by n factorial and then additionally multiply this 4 pi to the power n, this is just replacing this g times 4 pi. So you expanded that coupling, then it goes factorial, and then you divide, then it should go to some constant. And this is what you see, that indeed there is some alternation in n, but otherwise it's very, very constant. But if you have 400 terms, 1,000 digits, you can ask how constant it is. So it's important to know whether you divide by gamma n plus 1, or maybe this one is slightly different. So to know whether it's really factorial growing, then you have to analyze this series a bit more. And the way you do, you just switch on the odd combinations, and then it should be like no more alternating. It's some constant plus 1 over n plus 1 over n square and so on. And then you use this Richardson transformation on your series. You can kill actually the 1 over n behavior by this trick. And then if you apply many, many times, then you will see that this is really constant. So the asymptotic behavior is described exactly of this form. And now I would like to just give some general idea what we should do if the perturbative series grows like factorial. So how can we give a meaning of this series? So we have this perturbative series with growing coefficient. This function as it is meaningless. So what we will do, we already know if we divide by the factorial, then it's a meaningful series. So let's define a function with this meaningful series. This is called the Borel transform. So instead of this perturbative series, we go to a series when we divide by the factorial. Okay? This is called the Borel function. By construction, it has a convergence radius 1 in this case. So it has a finite radius of convergence. And then we would like to analytically continue this function and then use the inverse transformation, which would involve an integration on the real line. So if I take the Borel function, I analytically continue, I integrate in this way, then this should be a meaningful resummation of my perturbative series. This should give back the physical value. How to do an analytic continuation? One possible way is to use the Padé approximant. If we do the Padé approximant, then we will see the analytic structure, and what happens with this 400 coefficient if we repeat this analysis, then we see that the denominator will have some zeros, so we will have poles. Pole will condense starting on the real line, on the negative part starting at -1, and the positive starting at 2. So this is the analytic structure of the octagon, the Borel function of the octagon. But since we have some singularity on this positive line, we cannot just integrate there because there is a cut there, so we have to deform the contour. Either we integrate a bit above or below, but it will, so that there are two possible choices, and then we could just calculate the physical observable depending whether we integrate above and below. But clearly there is an ambiguity between the two, so we can ask, so what is the difference between these two integrations? And then the first contribution comes from the pole here. If you just pick up the residue of the pole, you see that the magnitude of this ambiguity is exponentially small.
So why only 2? You can also go zigzag between poles and other crazy trajectories.
Yeah. So this, what I'm indicating, that actually continuation will tell you that the cut is really starting here. And indeed, higher there are higher cuts. So you could go a bit above the first cut and jump below under the second. So you can play a lot with it. But naively, the simplest way is just to go above all the cuts or below all the cuts. I will show actually how to cook up an expression a series with these exponential corrections like this, such that it doesn't matter where you integrate. For each contour, I can tell you how to combine this exponentially small non-perturbative corrections such that the integral will always give the right physical value. Okay, so this was a bit naive way of getting some information about the analytic structure. Let's do it a little bit more seriously. And this is quite general, so let me just phrase it in such a generality. So we have a function whose perturbative expansion we calculated. This is the perturbative coupling, and these perturbative coefficients grow like factorial. So what we would like to do, divide by the factorial, go to the Borel function, and then we would like to understand the analytic structure of this Borel function. So the analytic structure is encoded, actually the large n behavior of the perturbative coefficient, or this divided by n factorial perturbative coefficient. So we haven't, say, an alternating part, and then we had this constant we have seen before, 1 over n correction, 1 over n times n minus 1, and so on. And then because we have a cut at 2, we expect that there is also in the asymptotics a suppressed 1 over 2 to the n term, multiplied with some constant, 1 over n, and these other corrections. So actually, if you already parameterized the perturbative coefficients in this way, we can plug back to the Borel function, and then we can just perform this summation one by one. If we sum the first term, we will see a pole at -1. If we sum the next term, we will see a log term at -1. If we sum the next, it's some function multiplying with the log. So if we calculate many of these terms, we will see a logarithmic cut and the function multiplying that logarithmic cut. This is called actually the alien derivative of the original function. Similarly, if we sum these guys up, we will see a pole at 2, we will see a logarithmic cut starting at 2, and the function multiplying with this logarithmic cut. Okay? So from the asymptotical behavior of the perturbative series, we could reconstruct the analytic structure on the Borel plane, and when we do the inverse Borel transformation, we would integrate a bit above, and we could see that this inverse Borel transformation will have some imaginary part. It shouldn't have, because the original determinant was real, but this imaginary part is non-perturbative, and the function which multiplies this leading non-perturbative piece, for example, it's exactly the same coefficient we have seen in the asymptotics. So the asymptotics of the perturbative series determines the non-perturbative correction, the perturbative expansion of the non-perturbative correction. So that's the message. And the theory which describes is the resurgence theory. So we have this numerical number, so let's try to fit actually the asymptotics. So I'm numerically fitting. So I told you this is the asymptotical behavior, yes, and then I have 400 coefficient, 1,000 digit. So I'm just using this Richardson transformation many times. I got a number like this, and I plug back to a web page what the mathematicians develop, and then it will give back the number. So there are such a nice pages, you plug back the number, and it gives back this -1 over 8 pi. And then you can go further, and then you can calculate the 1 over n correction, 1 over n times n minus 1, and so on. So you can, from the asymptotic behavior of the perturbative coefficient, knowing so precisely so many coefficients, you can fit all these numbers. And then you similarly fit all, so these are the alternating part, and then you can also fit the non-alternating part. So this means if I take the octagon, and I would like to get some physical value out of it, I calculate the Borel function, I reconstruct the logarithmic cut, I do the integration a bit above, and I will get non-perturbative correction of this sort, some imaginary part. So in order to have a real physical answer for the octagon, what I could calculate just by evaluating the determinant numerically, then I have to subtract that imaginary part. So instead of having the perturbative series resummed in this Borel way, integrating on the Borel plane, I have to subtract some non-perturbative correction times again a perturbative series which comes from the asymptotics, and this should be my observable. Okay? So the message is that the determinant, or this was actually the part of the determinant which had this large coupling expansion. So that part of the determinant is not just the perturbative series. It's not enough, because if you would resum in this Borel resummation, you will get an imaginary part. So I have to supplement the perturbative series with non-perturbative terms multiplied with the series expansion. And actually, this is also asymptotic, so I also have to add many, many terms. So I have to add a double series. First, a perturbative series in 1 over G, and also another series in the non-perturbative corrections. So this is called the trans series. I have infinitely many non-perturbative terms. I have each non-perturbative guy comes with its own perturbative series. The first is the original perturbative series, and the next is just the leading non-perturbative correction, the first cut contribution, and then these functions which multiplies the first cut, that perturbative series, was encoded in the large n asymptotics of that perturbative coefficient. So the large n asymptotics determines this first few coefficient in the first part, first non-perturbative correction, but it also determines actually the next one, the first few guys here. But this is also asymptotic, so we are supposed to calculate the large asymptotical behavior of that asymptotic series, and it will also tell us what is the real part on the second non-perturbative correction. So all these guys are very intimately related by this asymptotic relation. In order to go to very high orders, here we need many, many, many terms. And this is impossible. So in order to really calculate all these perturbative series, because this we would like, when we would like to describe a HUN-REN strong coupling expansion of our observable, we would like to provide all the non-perturbative correction with all these 1 over G expansions. So in order to do so, we have to connect the low order perturbative coefficients to low order non-perturbative coefficients, this green. These are called the bridge equation, and when we can have this bridge equation, we can calculate many of these terms, not just from the asymptotics fitting numerically. And this is possible, and I will explain. Just one interesting question what can appear here. Let's assume I know this perturbative series. Are all these non-perturbative corrections are determined uniquely or not? In some models they are not, in this actually they are. Okay, so how much time? Okay, so it's a bit technical, and then maybe I will not explain that much. What I would like to emphasize that you remember I already introduced this resolvent. It satisfies this differential equation, but additionally it also satisfies some integral equation. And then using this integral equation, one can actually come up a very nice trans series parametrization. What is relevant, if we take the symbol, and then this I already mentioned, this is the behavior of 1 minus the symbol around the origin. So that was this beta exponent. But the rest, we can make a kind of Wiener-Hopf decomposition, decompose into a function analytic on the upper half plane times another on the lower half plane, and we can parameterize this function with its zeros and poles. And what matters that all the non-perturbative corrections are related to the zeros of that function, of the Wiener-Hopf decomposition of the symbol. This will tell us where are the non-perturbative corrections. So once we know where are the non-perturbative corrections, we can parameterize them, and then we can plug back to the differential equation and then use the analytic structure of the resolvent, and we can relate all these non-perturbative corrections to each other. So we did it. In the simplest case of this flux tube correlator, they are very simple. There are non-perturbative correction at any order, but the function which multiplies these non-perturbative corrections is just one single term. There is no perturbative expansion there. So you couldn't do this asymptotic analysis in this sense, but we could calculate this coefficient, and you can just resum this series, and you got something what was known before. But we also did the octagon. So we calculated this, the first, second, and so on, maybe third, I don't remember, many non-perturbative correction, and then you could just calculate from this machinery what we developed, and they satisfied all these asymptotic relations. So the same number we calculated from the asymptotics, they come back also in this direct analytic calculation. Previously it was a fitting, but we can fix all these coefficients now. And we did also for this other localization result, which is related to the G minus G change of that observables. Okay. So the conclusion. I already mentioned, maybe that's the first conclusion, that I already mentioned I would like to understand maybe many others, also the analytic resurgence structure of QCD. So the resurgence structure of the octagon we understood, because we understood all the locations of the non-perturbative corrections, and we also learned how to calculate their own perturbative expansions. So that we did it for the octagon, but we did it very generally. So it's valid not only for the octagon, but all of these determinant expansions. So I'm foreseeing actually that by localization or other methods, many other determinants will appear with the Bessel kernel with the different symbols. And this generic approach will provide a strong coupling expansion for all those observables. So it's very general. Yes. And then what would be interesting to figure out? For example, we calculated directly the first few non-perturbative corrections, and then we can go as high order as we want, depending on the computer capacity. But it would be nice to see the generic structure, to find the basis of function in terms of which you can expand all these non-perturbative corrections. And in some other models, like for the free energy in the ON models or similar integrable two-dimensional models, we could actually complete this task, and we could calculate all the non-perturbative corrections explicitly. So it would be nice to see it here. In their cases, for example, the O-free theory, the perturbative coefficients didn't determine all the non-perturbative corrections. There were some instanton terms which were hidden for the perturbative calculations. But here in these observables for the octagon, the perturbation theory knows about all the non-perturbative corrections. This is quite interesting. So I hope there will be other observables, and one of them is, for example, this tilted Bessel tilted cusp anomalous dimension. That would be very nice to analyze. This method does not apply directly to that case, because what I described was a Bessel kernel where we had the same parity odd, or even, and then in this tilted cusps you also have odd, even, and it's more complicated. So thank you very much for your attention.
Thank you, Zoltan. Questions?
So morally speaking, the similar structure has this curvature functions, which are actually quite painful to expand. Mm-hmm. Do you think similar method could apply? Because like they also have similar Dresden phase type of integrals, which is essentially this Bessel G, if you do Fourier. Mm-hmm. So it would be interesting to see if you could apply.
Yes, but I think it's not an infinite determinant, but it's it's just an integral, or it's an integral equation. I don't remember this.
Yeah, it's like double integral, so it is even simpler than for you, I guess.
If it's just integral, I think you can expand it. But if it's
well, we tried to expand in, in usual pedestrian ways. It didn't quite work. And then some more philosophical questions. So what is this hope, big goal of this program, in the sense that obviously you need to have loss of order of perturbation theory as first condition, and second, you have to believe that it accounts for all the non-perturbative calculations. There is no way to check it. So neither of these.
Okay, so conceptually. So let's assume you have some physical observable and you expand that strong coupling. And then what we have seen, that this expansion, perturbative expansion, is asymptotic. So it grows like factorial. And then conceptually, I'm telling you that there is a theory behind what will tell you how to extract the physical observable to this completely meaningless looking factorially growing coefficient. And the answer is a trans series, okay? No, it's unique. So I'm telling you it's unique. Yeah, that's resurgent theory is telling you what is this prescription. What will give you a unique trans series. So you will have a trans series when you have the series, and then you have first non-perturbative correction with its series, and then if it's not, maybe it's worksheet instantons, I don't know, but you should think of as an instanton expansion. So your observable, if you expand that strong coupling, is the perturbative expansion, fluctuation around the perturbative point, and then you have the one instanton action and the perturbation around the one instanton.
You always can have the exponential suppressed function, which is invisible in perturbation theory.
You could, yeah, that's the point. So you could just add another exponential term, but you would never see. And that it wouldn't describe the physics. So somehow in this case, you know the determinant, so you could calculate the determinant numerically. So whenever you make some trick and you add ad hoc terms, that this will not reproduce your determinant. So what I'm saying, following the resurgence procedure from the perturbative series, it already, I can construct you the full trans series, all non-perturbative correction, which will reproduce the determinant, the physical observable.
Can I ask about the third point? So is there, you said that these techniques, this kind of determinants show up in many examples.
Yes.
Is there any example where we can make this third point, do any check of these worldsheet instantons, or even just, I probably forgot, but was it done in the past for any quantity? Did we ever match for circular Wilson line? Did anyone ever match any e to the minus squared lambda thing ever?
I mean, recently there was this integrated correlators, and then resurgence also showed up for the integrated correlators, and then they could really see that they are related to worksheet instantons. Here we didn't analyze yet, but I think somebody should analyze this question. Yeah.
There is a simple case, right? With just circular Wilson loop, and it is this with the Bessel function, which has an asymptotic expansion, and that one can associate with an instanton that wraps the sphere. This was done by Drucker many years ago.
Yeah, I should have, actually it was on the...
Think of it as a worldsheet that is not just a dome, but a dome plus something that wraps the sphere. I see, okay, thanks, nice.
Yeah.
So if there are no other questions, let's thank Zoltan again. And we are heading